my topic to be discussed is all about simple voltage connections. So what is simple connections? So if the line of action of the force acting on the connection passes through the center of the gravity of the connection, then each bolt can be assumed to resist an equal share of the load. The strength of the simple connection will be equal to the sum of the strengths of the individual bolts in the connection. So assume that these six circles right here is the bolts, and this small circle in the center is the centroid. So if PE or PU, if force PE or PU acts concurrent with this centroid right here, it is called simple connection. So the idea of the simple connection that all of these bolts right here carry the same amount of loads. So there are two ways of voltage connection. So the first one is the bearing type connection and the second one is the slip critical connection. So in bearing type connection, so there are no frictional resistance in the contact surfaces is assumed. So the second one is the slip critical connection, which it relies on friction. So when we say friction, it is the force resisting the relative motion between two surfaces in contact. So later on, I will give an example of these two ways of voltage connections. So moving on. So NECP 2001. So in gross area. So P is equals to 0.6 FYEG. So where AG is the gross sectional area, so to find AG is equals to width of the plate times the thickness. So next is the net area. So P is equals to 0.5 FU EN or the net area. So EN, to find EN is equals to width of the plate minus the number of holes times the bolt diameter plus 1.6 times the bolt diameter. So take note, the width of the bolt or rivet hole shall be taken as 1.6 mm greater than the nominal dimension of the hole. So that is why the bolt diameter will be added by 1.6. So allowable shear rupture. So if acting on the net shear area, so the formula to be used is F sub B equals to 0.30 FU. So if acting on the net tension area, the formula to be used is F sub B is equals to 0.50 FU. So moving on. So NSAP 2015. So gross sectional yielding. So P sub N is equals to FYEG. So where P sub N is the nominal strength and EG is the gross sectional area. So in gross sectional area, so we have LFRD and ASD. So LFRD pi is equals to 0.9 and in ASD omega is equals to 1.67. So next is the tensile rupture strength. So nominal strength is equals to FU A sub E. So in finding A sub E is equals to U times the net area. So where U is equals to the shear lag factor or 1.0. So to find the net area is equals to the gross sectional area minus the area of the holes. So to find the area of the holes is equals to the hole diameter times the thickness of plate times the number of bolts. So in tensile rupture strength, so there are also LFRD and ASD. So in LFRD, pi is equals to 0.75 and ASD, the omega is equals to 2. So next is the bearing. So bearing strength. So in bearing strength, there are three cases. So first, if deformation around bolt holes is a design consideration, so we must use this formula where the Rn is equals to 1.2 L sub C times T times FU less than or greater than 2.4 D times T FU. So second case, if deformation around bolt holes is not a design consideration, so we must use this formula. So Rn is equals to 1.5 L sub C times T Fu less than or equal to 3.0 times D times T Fu. So the third case is for bolts used in a long slotted hose or slot being perpendicular to the forces, so we must use this formula. So Rn is equals to 1.0 L sub C times T Fu less than or equal 2.0 D times T Fu. So in LFRD, phi is equals to 0.75 and ESD is equals to omega is equals to 2. So in here, so the nominal strength is equals to FNB times ATB. So where FNB is the stress on bolts and the E sub TB is equals to the area of bolts times the number of bolts. Proceed to example number 1. So give the following data of the slip critical tension connection. So plate A36. So given ang Fy and Fu. So Fy is equals to 248 MPa and Fu is 400 megapascals. So in bolts, 22 millimeter diameter, E325 in standard holes with threads excluded from shear planes. So the given and dead load, which is 360 kilonewton. So considering the plates only, compute the safe live load using NSCP 2001. Proceed to example number 1. So give the following data of the slip critical tension connection. So plate A36. So given ang Fy and Fu. So Fy is equals to 248 MPa and Fu is 400 megapascals. So in bolts, 22 millimeter diameter, E325 in standard holes with threads excluded from shear planes. So the given and dead load, which is 360 kilonewton. So considering the plates only, compute the safe live load using NSCP 2001. So the given are Fy is equals to 248 MPa, Fu is equals to 400 MPa, the bolt diameter is equals to 22 mm, the hole diameter is equals to 26 mm, the dead load is equals to 360 kilonewton, the width of the plate is 280 mm, and the thickness of the plate is 12 mm. So this is a slip critical type connection. So the problem is to find the safest live load using NSCP 2001. So first is we must find the gross area. So find the gross area. The formula is P is equals to 0.6 FYEG. So given Fy, so substitute. So 0.6 Fy is 248. So to find the gross sectional area is width of the plate times thickness, which is 280 times 12. So compute. So 0.6 times 248 times 280 times 12. So P is equals to 499.968 kilo Newton. So for net area, so the formula is P is equals to 0.5 Fu E sub N. So first is we must find area net since Fu is given. So area net is equals to 280, which is the width of the plate, minus 2 times 24 plus 1.6 times 22. So compute 280 minus 2 times 24 plus 6 times 22 equals, so the area net is equals to 5033.6 mm squared. So substitute, so P is equals to 0.5, FU is 400, and our net area is 5033.6. So P is equals to 0.5 times 400 times 5033.6. So our net area, our P in net area is 1006.72 kilo Newton. So next is all about block shear. Block shear. So first, let's consider if this plate is pulled to the right, this plate is pulled to the right, the one possible path, shear rupture, shear is right here, then the tension is right here. So if we draw this, so it will look like this. So na siya. So these are the bolts. So the distance from there right here is this. So 120 plus 80, which is 200 mm. So the distance from there to there is also 80 plus 80 plus 40, which is also 200. So first is we must find the tension area. So 200 minus 2.5 times 24 plus 1.6 times 22. So compute 200 minus 2.5 so 2,992. So for area for shear area is 200 minus 2.5 4 plus 1.6. So same, since the same man sila, so 2,992 iyang area. So from the formula that we discussed earlier, so in acting on net tension area, so P is equals to 0.5 times 400 times the net area, which is our tension area, which is 2,992. So plus acting on shear area, so 0.3 times 400 multiply by 2,992, which is the shear area. So our P now is so 957.44 kN. So if we get a summary of this from gross area to block shear. So for gross area is P is equals to 499.968. For net area, P is equals to 1006.72 kN, and for block shear is 957.44 kN. So if we find the cheapest P, so we must choose the smallest P. So this, so our safe P is 499.968 kN. So the problem is to find the safe live load. So P sub T is equals to P D plus PL. So greater less than or equal to 499.968. So since given undead load which is 360, then PL so PL is our dead load which is 300, or our one is which is 499.968 minus our dead load which is 360. So our live load is less than or equal to, so compute. So 499.968 minus 360. So our live load is 139.968 kilo Newton. So given the following data of the bearing type connection, so plate A36, so Fy is equals to 248 MPa, Fu is equals to 400 MPa, Fnb is equals to 457 MPa. So the bolts, so 22 mm diameter, A325 picks in standard holes with threads excluded from shear planes. Assume that the deformation at bolt holes are a design consideration. So determine the design strength and allowable strength using NECP 2015. So this from the illustration, so this is a bearing type connection. So when we say design strength, it is in LFRD, and this allowable strength is in ASD. So from the problem, the given are Fy is equals to 248 MPa, Fu is equals to 400 MPa, Fnb is equals to 457 MPa, the bolt diameter is equals to 22 mm, the hole diameter is equals to 26 mm, the weight of the plate is 400 mm, and the thickness of the plates which is 12 mm. So the problem says is to use NECP 2015. So to find, first is we must find the gross sectional area, sectional yielding, I mean. So to find the formula in finding the gross sectional yielding is nominal strength or Pn times Fyag. So given Fy, so which is 248, so the gross sectional area, so which is the weight of the plate which is 400 multiplied by the thickness of the plate which is 12. So compute, so 248 times, so the answer is 1190.4 kilo Newton. So the problem is to determine the design strength and the allowable strength. So we must find the LFRD and ASD. So in LFRD, so PU is equals to pi Pn. So the value of pi is 0.9. So in ASD, omega is 1.67. So to find PA is equals to nominal strength over omega. So first is we must find PU. So PU substitute 0.9 times 1190.4. So 1071.36 is our PU. So our PA is 1190.4 over 1.67. So compute. So the answer is 712. So our PA is 712.81 kilo Newton. So erase. So the second find is the tensile rupture strength. So to find the tensile rupture strength, so the formula to be used is nominal strength Pn, P sub n is equals to Fu E sub A. So since given ang Fu, so we must find the A sub A. So to find E sub A, so from the our previous discussion, so E sub A is equals to U over N, U times E sub N. So which is U is the shear lag factor, which is 1.0. So nominal strength Fu, which is 400, so substitute. So U is 1.0 multiply by the width of the plate, which is 400, times the 12, which is the thickness of the plate, minus the whole diameter, which is 26 mm, times the thickness of the plate, which is 12, times 2. So upon solving, we can get 400 So 1000 P sub n nato is 1670.4 kilo Newton. So in LFRD, so in tensile rupture strength, so the pi is 0.75. So 0.75 multiplied by 1670.4. So the answer is 1252.9 kilo Newton. So in ASD, so omega is equals to 2. So P yun sa LFRD. So PA is equals to PN over omega. So 1670.4 over 1.6 over 2. So PA is equals to 835.2 kilo Newton. So next is bearing. So from the problem, it says that the deformation around bolt holes is a design consideration. So from our discussion, so there are three cases. So since the problem says that the deformation around bolt holes is a design consideration, so we must use the formula Rn is equals to 1.2 L sub C times T Fu less than or equal to 2.4 D times T Fu. So Rn is equals to 1.2 L sub C times T Fu for dt Fu. So since all of these are given except L sub C, so we must find first L sub C. So to find L sub C is the distance of the bolts, so which is 100 minus the bolt hole diameter, which is 26, times the number of bolts, which is 2 over 2. So find LC. So we can get 74. So we can now proceed. So substitute. So 1.2 times 74 times the thickness of the plate, which is 12, Fu, which is 400, so less than or equal to 2.4. So the diameter of the bolt, which is 22, times the thickness of the plate T, which is 12, times Fu, which is 400. So compute. So we can get 426.24. So less than or equal to 253.44 kilo Newton. So in this case is we must choose the lesser one, which is 253.44 kN. So Rn is equals to 253.44 so times the number of bolts of all bolts, which is 4. So our Rn now is 253.44 times 4 can get 1013.76 kilo Newton. So to find LFRD and ESD, so LFRD, so pi is equals to 0.75, so multiply by 0.75, so we can get the PU. So pi RN is equals to 0.75 times 1013.76 is equals to 760.32 kilo Newton. So in ESD, so the omega is equals to 2. So Rn over omega. So 1013.76 over 2. So we can get so we can get 506.88 kilo Newton. So let's proceed now to shear. So erase. So to find shear, so the formula is Rn is equals to FNB times area T sub B. So since given ang FNB, which is 457 MPa, so to find the area of the bolt, so pi over 4 So times the diameter of the d squared times the number of bolt. So times the number of bolt, which is 4. So substitute 457 pi over 4 times the diameter of the bolt, which is 22 squared times 4. So compute the Rn. So 457 times pi over 4 times 22 squared times 4. So you can get 694.882 kilo Newton. So LFRD, so pi is equals to 0.75. So PU is equals to pi PN pi RN. So 0.75 multiplied by 674, six 4.882. So we can get 521.16 kilonewton. So in ESD, so 694, so the omega is 2, so 882 over 2, so we can get, so 347.4415 kilo Newton. So next is we get the summary of our answers. So from gross sectional yielding to shear. So summary. So NGSY, or the gross sectional yielding, the LFRD is 1071.36 kilo Newton. Then the ASD is 712.81 kilo Newton. So from tensile rupture strength, o TRS, so LFRD is 1252.8 kilo Newton. So in ASD is 835.2 kilo Newton. So in bearing, so in LFRD 760.32 kilo Newton. So in ASD is 506.88 kilo Newton. So in shear, so in LFRD is 521.16 kilo Newton. In ASD is 347.44 kN. So the problem is to find the design strength and allowable strength. So to find the design strength and allowable strength, so we must choose the lesser one. So in LFRD is the design strength is 512.16 kN, and in ASD the allowable strength is 347.44 kN.